Boa tarde a todos. Vamos a comenzar hoy, continuando con un curso que está administrando, el curso que el profesor Paul está administrando en nuestra institución. Esta quinta parte debe tener aproximadamente 40 minutos de duración. Después de 40 minutos vamos a dar una parada de 10 minutos y continuaremos con la sexta parte, que sería otros 40 minutos. Entonces, voy a pasar la palabra para el profesor Paul para ele começar a sua apresentação. Um momento. Ok, professor.
Welcome to everybody. We continue the series of lectures on chalcones, on chemistry, physicochemical characterization, and biological actions. The first lecture today will concentrate on physicochemical characterization of chalcones and cyclic chalcone analogs, and one of the most common was one of the most important chemical reactions of the compounds. They are radical scavenger activities. As we have shown before, the chalcone structure can be divided into three different parts: the two aromatic rings and the three-carbon linker, which is an enone system, which is a polarized enone system in which the alpha and the beta carbon atoms have got different polarity, and due to this polarization of the double bond, the carbon-carbon double bond can react with nucleophilic centers as well. Let's have a short look at the synthesis of chalcones and analogs of chalcones. In this lecture, only the Glaser-Schmidt condensation is repeated, since one of the previous lectures were already reviewed all the 6 important synthetic methods listed in this screen. As for the Glaser-Schmidt condensation reaction, in order to synthesize chalcones, involves condensation of substituted acetophenones with substituted benzaldehyde to yield the expected chalcone structure, and the reaction can be performed by means of acid catalysis and base catalysis as well. Sometimes, typically based on the substituents of the aldehyde, the aromatic aldehyde, the acid catalysis or the base catalysis gives the higher yield and purer final product. Just refresh your memory on the stereochemistry of chalcones. The stereochemistry of chalcone basically determines by that of the enone moiety, in which in the most stable, energetically most favored conformation and configuration, the carbon-carbon double bond has got trans configuration, and the sigma bond has got S-cis conformation or configuration, because under normal conditions the sigma bond structure, configuration of the sigma bond is stable. In some particular cases, in particular substitution of the rings and or the carbon-carbon double bond, however, the S-trans conformation could be the preferred conformation of the cycle of of the chalcone units. In this lecture, we will show some physical-chemical characterization of not only the open chain chalcones, which are analogs of the natural ones, however, several cyclic analogs of them with carbo cycles and with heterocycles. The carbocyclic derivatives can have 5-membered ring, 6-membered ring, and or 7-membered ring. And in case of the heteroanalogs of the 6-membered cyclic chalcone analogs, we will show results with those ones in which oxygen or sulfur atoms are incorporated. We also been synthesized ferrocene analogs of chalcones. However, because of the high electron density of ferrocenes and electron donating capacity of the ferrocene unit, the polarization of the carbon-carbon double bond is minimized. And that's why the reactivity of the compounds with nucleophilic reagents diminished. Why to synthesize and why to analyze cyclic chalcones? As we can see on this molecular mechanics calculations, the three-dimensional structure of the chalcone analogs with 5-membered rings, the blue one, with 6-membered ring, the red one, and with 7-membered ring, the green one, is fairly different. So it means one of the most obvious consequence of incorporation of a ring into the open chain chalcone structure is modifying the three-dimensional structure of the compounds, particularly modifying the relative position of the two aromatic rings of the chalcone moiety. The first set of investigations were aimed to see how efficiently the electronic effect of the aromatic substitution of the benzylidene moiety is transmitted through the conjugated system up to the carbon-carbon. In this way, this spectroscopic method can help us to and give us information, help us to characterize and give information on the planarity of the chalcone moiety, since the higher the efficiency of the electronic effects of the substituents, the more planar is the compound. In other words, the stronger the conjugation. Analysis of electronic effects can be performed by so-called single substituent parameter method or dual substituent parameter methods. In the first case, we are using only one set of substituents, which involves both the inductive and the resonance effects of substituents. In the dual substituent parameters, we are using parameters which separately characterizes the inductive and the resonance effects of one particular substituent. Our result showed by infrared spectroscopic result based on the resonance frequency of the carbon-oxygen double bond, I mean the carbonyl group, showed that the efficiency of the transmission of the substituent effects is the highest in the Indanon series, where the raw value of the linear equation had got the highest one. Afterwards, we found the most efficient system is the chalcone system. It means that the open chain chalcone system and the 5-member ring chalcone system are the most planar series in which the efficiency of the transmission of the substituents are the highest one. In case of tetralone series, where the ring size is 6, and in the benzo-subalone series, when the ring size is 7, due to the higher conformational mobility of the cyclic rings, you see, the efficiency of transmission is lower as we expected, and rather similar to each other. X-ray diffraction studies of the benzos among the derivatives of the benzo-suberon series. Those are the derivatives with the largest carbocyclic rings we have been investigated so far. We can see that when in one series of cyclic chalcones, when we have a constant ring size, not only the ring size, however, the substitution of the compounds also determines the three-dimensional shape of the molecules. And this difference in the three-dimensional shape is responsible for the different efficiency of the transmission of the effects, the different degree of conjugation, and as a final, the different reactivity of the carbonyl-carbon and the carbon-carbon double bond of the cyclic chalcone analogs. After completing the studies on investigating the electronic structure of the compounds, we have been concentrating on another physicochemical characteristics of the compounds, namely the lipophilic character or lipophilicity of the cyclic chalcones and their cyclic chalcone analogs. What lipophilicity is and why we determined the lipophilic character of the compounds. Lipophilicity is a very important, from biological point of view, a very important physicochemical characteristics of any xenobiotics, which characterizes the affinity of one particular compound towards the lipophilic phase of a separated two-phase system. The lipophilicity is nothing else than the logarithmic value of the equilibrium concentration of the compounds in the organic phase and the aqueous phase. And in practice, the most common log-P determinations were performed using one octanol as a lipophilic phase, lipidic phase, and water and or a buffered aqueous solution as the aqueous phase. The log-P values were determined were determined in 1 octanol because using this organic compound, organic solvent, the obtained log P values showed relatively high, the highest correlation with the biological activities of the investigated compounds. As for the experimental determination of log P values of foreign compounds, the classical gold standard, so-called gold standard determination, is the shake flask method. The shake flask method is very precise, however, needs extremely pure compounds, sometimes takes time, and needs very developed sensitive analytical methods, in particular in those cases when the log P values are very, very high. Indirect determination of log P can be performed and has been performed by reverse phase thin layer chromatographic analysis, reverse phase HPLC analysis, or capillary electrophoretic investigations of the compound. Besides the experimental methods, several computational methods are also used in use to calculate the lipophilicity of different organic compounds. We have used reversed phase, validated reversed phase thin layer chromatographic methods to investigate the log P values in the 4 series, namely in the open chain chalcone series, the 5-membered ring cyclic analogs, the 6-membered ring cyclic analogs, and the 7-membered ring cyclic analogs, with the same set of substituents on the benzylidene moiety of the derivatives. Our experimental results showed that the log P values, the lipophilicity of the compounds, continuously increasing as you incorporate a higher and higher number of CHT units into the molecules. So, for example, if you can compare the log P values of the unsubstituted derivatives, we can see that the lowest log P value can be found in the open chain compound, and the log P value of the 5-membered, the 6-membered, and the 7-membered ring derivatives are continuously increasing. Such an increase could be observed in all the investigated substituents. We can see. So generally could be stated that by means of incorporation of the methylene units, I mean incorporation of a ring into the open chain cyclic chalcone structure, not only the electronic structure has been changed, but the lipophilicity of the compound is also changed. In case of a particular series, namely in the case of the series of the 7-membered ring analogs, we also investigating how the log P values with different substitutions on the benzylidene unit changing in this particular series of cyclic chalcone analogs. We could see that the absolute, I mean the relative values of these are absolute values, but the relative values of the compounds log P values of the compounds in the ortho, meta, and para substituted derivatives are very close to each other. However, changing one substituent to the other, the log P value of the compounds can be sometimes definitely be changed. So, as a conclusion of your experiments, to obtain an optimal log P values from the biological activities, we can tune the log P value of the cyclic chalcone analogs by means of changing the ring size and changing the substituent as well. As it was mentioned in the first lecture of this series, the compounds can undergo easy isomerization. And we also investigated how the isomerization, the EZ isomerization of the seven-membered ring series has been changed using or validated reverse phase thin layer chromatography method. As we can see, that the log P of the E isomers were found higher in each substituent than the respective Z ones. Or in other words, the Z isomers were always less lipophilic, more water soluble, in other words, than the starting E isomers. So this is the chart summarizing the most important reaction of chalcones involving the Michael addition, the double bond isomerization, and the radical scavenging activity. And in the rest of this lecture, I will discuss the radical scavenging activity of chalcones and aromatic compounds in general. Radicals are very toxic species when they are formed in biological systems. However, radicals are formed not only in biological systems, however, in non-biological systems as well, and the radicals formed are destroy, chemically modify the sensitive compounds, mainly those with conjugated double bonds and polyhydroxy substituted aromatics. When we're taking into consideration the possible reaction paths of the reaction of chalcones with different radicals, we can take into consideration reaction of the radical with the carbon-carbon double bond as a high electron density unit, and obviously both aromatic rings of the chalcone molecule. Since under biological conditions, the most reactive radical formed is the hydroxyl radical, we were mainly interested in the reactivity of aromatics and chalcone derivatives with hydroxyl radicals. If we survey the literature, we can find experimental and theoretical works discussing of the reaction of hydroxyl radicals with non-hydroxylated aromatic compounds. The simplest example of this type of aromatics is toluene. When the reaction of toluene with hydroxyl radicals were formed, 4 different pathways were taken into consideration. Namely, reaction of hydroxyl radicals with the aromatic rings, attacking the aromatic ring at ortho, in meta, or para position, and attacking the methyl group as a aliphatic part of the toluene, generating a carbon-centered radical by means of hydrogen atom abstraction. Experimental results showed that when we have an aromatic ring with a non-hydroxyl substitution, the preferred reaction is the substitution of the aromatic ring in ortho position in respect to the aliphatic substitution. Of course, not only this product is not the only product according to the experiments and according to the calculation, the theoretical calculation. However, these products seem to be the main products formed under the experimental conditions in which the hydroxyl radicals were generated by means of UV irradiation in the presence of nitrate ions. The hydrogen abstraction reaction with the methyl substituents were also observed, and analysis of the mixtures showed that the primary product, the methylene radical, the carbon-centered radical, is readily react with molecular oxygen, forming further derivatives which undergo a variety of decomposition reactions. Here is a chart which showing the primary products, I mean the ortho substituted, ring substituted derivatives, plus the carbon-centered radicals, the methylene derivatives, which can further react with molecular oxygen, resulting in a variety of decomposition products listed in this chart. Other authors also investigated the effects of substituents, on the reactivity of benzene derivatives with non-hydroxyl substitution. They found that if they compared the pseudo first-order rate constants associated with degradation of benzene of the derivatives through the experiments in which hydroxyl radicals were generated by UV irradiation of hydrogen peroxide, the comparison showed that the rate of the reaction increased when alkyl substituents and or electron pair donating substituents can be found in the aromatic ring. In other words, this type of substitution by means of increasing the electron density of the aromatic ring increased the hydroxyl radical reactivity of the derivatives as well. Then we are talking about natural chalcones and natural chalcone analogs, generally speaking, flavonoids. We can see that among the natural derivatives, most of them are hydroxyl substituted and or methoxy substituted derivatives. Experiments and theoretical calculations showed that when the aromatic ring possesses hydroxyl substitution, the radicals, among them the hydroxyl radicals, primarily attack the hydroxyl group. As a result of this attack, different mechanisms were identified, and these different mechanisms showed correlation with different physicochemical parameters of the phenolic compounds, the phenolic antioxidants. The two most common experimental mechanism of reaction of phenolic antioxidants involving chalcones with radicals, hydroxyl radicals, are the so-called hydrogen atom transfer mechanisms and the single electron transfer mechanisms. The two equations showing the essence of these two mechanisms are shown in this chart. And as we can see, in the first case, a hydrogen atom is transferred from the hydroxyl group to the radical, resulting in a neutral molecule, a neutral species, and generating an aryl oxy radical, which is due to the delocalization, are much more stable, much less reactive radical than the original hydroxyl radical. The single electron transfer mechanisms involves one electron transfer of one electron from the aromatic phenolic compound, the phenolic compound, and when one electron is transferred, the original radical is converted into an anion, and as a result, the phenolic compounds converted into a radical with a positive charge. Theoretically approaching these two methods, experiments showed that in the first case, in the hydrogen atom transfer mechanisms, it is the bound dissociation enthalpy which shows the highest correlation with the reactivity, radical scavenger activity of the compounds, while in the single electron transfer mechanisms, it's the adiabatic ionization potential. In another two method, the other two mechanisms, which could also occur in reactions of radicals and aromatic phenolic compounds, aromatic antioxidants, is the single electron transfer followed by proton transfer and the sequential proton loss and electron transfer, whose complex mechanisms are represented here by two consecutive equations. And in the first case, it is the adiabatic ionization potential and the proton dissociation enthalpy, while in the second case, it is the proton affinity and the proton dissociation enthalpy is the relevant physicochemical parameter. The hydroxyl radical scavenger activity of hydroxylated aromatics are frequently manifested by means of complex formation, typically chelate complex formation of transition metals. transition metals can form reversible redox systems under physiological conditions, and due to their redox properties, they can react with hydrogen peroxide, and this reaction, which is frequently referred to as the Fenton reaction, hydroxyl radicals is formed. Since hydrogen peroxide is formed under physiological biochemical processes, that's why the non-complex transition metal ions represent a threat for the cellular macromolecules, since hydroxyl radicals are formed. To prevent this reaction, hydroxylated aromatics, typically polyhydroxylated aromatics, can form complexes with the metal ions, generally by means of involving the deprotonated form of them, and as a result of the chelation, its redox potential of the transition metal ions, and that's why the reactivity towards hydrogen peroxide is decreasing. So these are the five most common mechanisms of action in which the hydroxylated aromatics involving hydroxyl substituted flavonoids, chalcones, can exert their antioxidant capacity. In the referred article, Martin Seth and co-worker reported that the most effective scavenger of hypochlorous acid dependent of radicals generated from hypochlorous acid is those ones which have got the substitution pattern represented by the compound titled 5B. So this is the general approach to increase the hydroxyl radical scavenger activity of chalcones and chalcone analogs. In our own experiments, we investigated the hydroxyl substituted derivatives of the open chain chalcone and the 5-membered ring, 6-membered ring, and 7-membered ring analog of chalcones, and compared it with the known natural antioxidant quercetin. According to our experimental results, using the Fenton reaction and following the reactivity of the compounds as a function of time, we found that the most effective antioxidants were the 5-membered ring methoxy substituted compounds, 2A, the 5-membered ring hydroxyl substituted compounds, the 2B, and the 7-membered ring hydroxyl substituted derivatives. So our experiments with these cyclic chalcone analogs are in according, our experimental results with our cyclic chalcone analogs are in accord with those results previously obtained, previously reported for the open chain chalcones. Thank you very much. That was the most some selected examples concerning the physicochemical representation and radical scavenger activity of chalcones and cyclic chalcone analogs. Thank you for your attention.
Bom, boa tarde para todos novamente. Agora foi que eu coloquei o link para vocês poderem assinar a presença nesta do formulário para vocês poderem preencher ele e enviar para nós. Nós vamos agora ficar 15 minutos de parada, e então às 5 para as 3 horas, é decir, às 2h55, vamos voltar com a última parte do mini curso. Espero que todos estejam gostando e, bom, até a nossa próxima aula, que será daqui a pouco. Obrigada a todos e até lá.